All right, happy Friday, everyone. Today is September 9th, and this is episode 23 on all things DOCSIS. I'm Brady Volpe, founder of the Volpe firm, and Nimble This. Today, we have a fantastic episode for you on PNM 3.0, 2016 advances in technology, and what to expect coming in 2017. But first, let me introduce our panelists for today's show. With us, we have the diviner of DOCSIS, John Downey, CMTS, technical leader at Cisco Systems. John, great to have you with us today.
It's good to be back, as usual.
Yes, and you have fantastic audio as always. Also with us, for the first time in the show, we have the Ayatollah of Rock and Rolla for proactive network maintenance, the one and only Larry Wolcott, Comcast Fellow in Operations Technology. Larry, so good to have you with us today.
What an introduction. The Rock and Rolla Ayatollah.
Ayatollah of Rock and Rolla.
I love you.
John, you ready?
I love it. Okay, that's great. So it's great to be here. I've been a big fan of you guys for a long time. Obviously, my heart and soul is in this PNM stuff. A cable junkie from the get-go, and it's an honor to be here. Really excited to have some fun with you guys and talk about this great stuff.
Yeah, so fantastic. So we're obviously, this discussion topic today is going to be around proactive network maintenance, aka PNM. I would like to start and open up the discussion just to kind of talk about how far we've come from the early days of PNM. From where we were just looking at pre-equalization values from the cable modem itself to now where we are today, where we have full band capture, where we're looking at downstream spectrum, we're doing upstream spectrum analysis, we're looking at intermittent modem capabilities to find noise. So I mean, we're almost changing the term of PNM to maybe some new name like PNM Plus or Advanced PM, because we're doing so much more with PNM, and I think we're getting just so many more capabilities, and so this is some of the things I want us to cover in today's meeting. Do you guys agree?
Absolutely, great stuff, Brady.
John, good, yeah. All right, so Larry, maybe we can start with you. I know you're doing some pretty good, cool things and stuff. Is there any particular item you want to open up with?
Yeah, actually, it's funny. You look at the board behind me here. I'm actually squatting in a conference room at Cable Lab. So all that cool formulas and jazz back there is not mine. I can't take credit for it, but it's like the perfect scenario for doing this kind of thing with you guys, and so appropriate. That looks like a 3.10 FM. But let's roll back into the PNM time machine to 2000. No, let's go to 1999. And just for a quick history lesson on this stuff. Adaptive equalization coefficients are where this all started. Can you see an echo tunnel between the cable modem and the CMTS on the transmission line, and then what, right? And that's where this whole thing started in '99 with DOCSIS 1.1. And I remember distinctly when this came out, kind of looking at it, had no idea what it really meant, which was funny. And then I kind of shook my head, and the problem with PNM or with adaptive equalization at the time was they used this 8-tap equalization structure, and the resolution was horrible, and that was really the first technical constraint. And then really more so the problem with it was the early implementations of equalization were just really bad. We turned it on and customers wouldn't come online, and just lots of bad stuff happened. And equalization just started off with a bad name, and it took years to overcome the stigma that was created by the early implementations. And here we are today. If you look at, number one, just equalization as a concept, we can't function 64 QAM reliably without it. And if you look at the pre and post constellation and MER that we see today in many, many areas of our network, it's a must. We just couldn't do what we can do, deliver the quality and amount of service that we do without it. And the evolution from 1999 till today, and all of the folly in between in terms of industry adoption and operational adoption and learning and evolution is remarkable. And I remember very fondly when I first saw how this could be operationalized in 2007 when I was visited by Alberto Campos and Eduardo Cardona. they came and visited and showed me the spreadsheet. Brady, have you ever seen Alberto's spreadsheet?
I don't know that I saw one that he had on PNM. I did see Alberto's early presentations at Cable Tech Expo on PNM, and I think it was a similar thing as you said, where I had no idea what he was talking about. So
yeah, exactly. And the crazy thing is, it's kind of history repeats itself. And now that we've operationalized it, it's in the tools, alarms pop, and people are dispatched to go fix stuff. And still to this day, I got to be careful when I say this, the interpretation of that information is very difficult. And that's kind of the opportunity, and this is a great segue into the evolution of where we're at and where we're going in the future, and machine learning and all this cool stuff we're going to talk about how do you interpret the data and what do you do with it, and actionability, and how do you translate that into business and how you operate your cable system. It's such a fantastic topic.
Let me throw in some historical data too, or my 2 cents. And I know I've talked about it before with you and Brady. Cisco is one of the only ones that used a TI Intel CMTS chip. Everyone else was Broadcom. And we ran into some issues with adaptive EQ, or actually pre-EQ, the 8-tap equalizer. And what we found out was that when you have different firmware, you might have impulse noise. The pre-EQ could get out of whack. Meaning, I'll give you an example. Say my MER, my upstream MER says 20 dB. I turn on pre-EQ, it goes to 25. A week later, it drops down to 17. We're like, wait a minute, what's going on? Turns out the pre-EQ is like pre-equalizing the wrong way, or out of time, getting the wrong coefficients. So Cisco a while back made a decision that we'd have like a catch-all. On the CMTS, by default, we have this on once you turn on pre-EQ, because pre-EQ is not on by default for the CMTS, for our CMTS. Once you turn on pre-EQ, if the MER of a single modem drops by more than 3 dB, we kind of attribute it to pre-EQ problems. So we send a direct load to the modem, basically saying, clean yourself out and start over again. So it actually works well as kind of a catch-all, Band-Aid, if you will. I don't know if Aris has the same thing. Maybe they do. But it's actually helped save me quite a few times.
That's good to know, John. Many years of doing this, and I've seen the behavior. I didn't know exactly why, and you just explained it. I should come to these more often. All right, cool. So anyway, it was, and then to basically just rein that in a little bit, that was some of the history. We started with the first Scout Flux implementation. That's our first crack at, hey, here's equalizers. We didn't really know what the heck it was going to tell us or what we're going to do about it, but it was kind of the first output of that coefficient analysis. And we just kind of quietly put a little cool-looking equalizer button in the tools, and it just let people stumble on it with no fanfare, no training. I mean, we did a couple of decks that talked about what the equalizers did and how to interpret it. We didn't really know. And then just kind of out of grassroots from the field, which is really, I think, the secret sauce to our success for the program, the technicians started picking up that cared enough about it and started engaging us by email and calling us and creating relationships to the field. And that was a kind of an early implementation of this DevOps model by happy accident, if you will. I still have fantastic relationships with a lot of folks out in the field, and a very cohesive feedback and development life cycle, so that if something happens or a feature or function, it's just magic when you get close to the field and respond quickly to that. But so we turned it on in 2009, 10 years, ironically, after the very first equalization implementation. 10 years after that, after having it out there and running, we figured out how to operationalize it. And then along with that came all of the trials and tribulations of now what? And it's the now what where things get interesting. And Brady, let me hand it back to you. You deal with the now what every day of your life with your Nimble products and out there with the operators. Anything to add?
Well, yeah, I mean, so we got involved, I think it was around 2011. I had seen, as I said, I didn't understand it with Alberto's original presentations. because they were very technical. But I think it was when Cable Labs came out with their reference implementation around 2011 that we got involved. And the reference implementation really helped understand how you put this long EQ string into their reference implementation. You get out the taps, you get out the in-channel frequency response, and that actually made sense. The challenge with the reference implementation is it wasn't operational. So then we started NimbleThis, and we turned the reference implementation into something that had a database behind it, something that had you could start importing data, SNMP, polling modems and CMTSs. And then we started working with some small cable operators to really say, okay, we see these problems. Let's see if we can actually go out and find where the problem is in the field. And that's where it started to become really exciting for us. But the challenge then it became after that was there were so many modems that were sort of non-compliant, where we would pull the modem and we would get back and Larry, I think you coined the term, a bunk equalizer string. And I really like that. So you kind of had to build up this library over time of, if this modem, then that. So you can start dispelling it. You can start training cable operators that, how to turn on pre-EQ, how to put the CMTS into TDMA mode, because if it's in TDMA mode only, the modems are operating as a DOCSIS 1.1 modem. They're not taking advantage of their 2.0 or 3.0 capabilities. So there was, both a learning curve for us as a commercial PNM provider, and also the cable operators, as some of the things that they were doing weren't taking full advantage of the pre-equalization in the cable modem. So, it's one thing to just understand the fundamental technologies of pre-equalization. Then it's another thing to understand the limitations, because none of this was part of the DOCSIS specification. So there were so many issues in cable modems not fully supporting it that we later fixed. I think you guys drove a lot of this in fixing issues in the firmware and the modems and CMTSs, and us also working with vendors, and then also training cable operators on how to optimize their systems and taking advantage of this. And again, this is still classic PNM. So it was really exciting then also to say that now in the DOCSIS 3.1 spec, all this is going to be standard. So huge learning curve for both us and operators, and as you said, getting this operationalized within cable operators. So it's cable operators really understand how to be reactive. When a modem's offline, we know we got to fix that right away. But it's completely different to say be proactive, where we'd really like not to have the cable modems go offline. We'd like to fix these before the subscriber is impacted. So that's a big shift within organizations, and getting there takes a lot of work internally, working with operators.
Yep, absolutely. John, talk a little bit about your early introduction to PNM and equalization, using them and what was your reaction at the time?
I was going to add on to Brady's PNM, reactive RNM. Everyone does RNM, reactive network maintenance. So when PNM came out,
it's called network maintenance, yeah.
In the cable industry was C-Core Electronics, and then I went to WaveTech, and so I had a lot of background in upstream, downstream sweeping, and we used to do this way back in the day. We called it basically FDR, frequency domain reflectometry. Basically, you're doing an upstream sweep with really tight granularity on your sweep points, avoiding overlapping with actual channels. But if I made my sweep points tight enough, I could get better granularity in my sweep response. And looking at an upstream sweep trace, I could see standing waves. I could use the well-known formula, 492 times velocity propagation divided by the delta in the frequency standing wave, and find out the distance to the fault. So I was well aware of troubleshooting that way. But now that we have so many modems in the field doing this already, we could utilize and exploit that functionality, right? So the more modems we have, the more test equipment, the more visibility we have out in the field. So when I started seeing, and I was thinking at that SCTE Expo years ago where Alberto was showing this stuff, and I was like, this is pretty cool. And then I think there was a winter or summer conference for Cable Labs out in outside of Denver. Keystone? I think it was in Keystone a few years back. And he was showing me some of the functionality, and I was like, yeah, this is pretty powerful stuff. It's just a matter of operationalizing it, like Brady was talking about. You can put a paper out on the web and people look at it like it's Greek, right? The smaller operators didn't know what to do with it. you work for Comcast, so you're a bigger operator. You have S&P expertise, a little bit more resources that can go into it. So you guys really ran with it, and I was pleasantly surprised. Now I got everyone else asking, well, how can I get that functionality as well? How can I get visibility into what's happening out in the field? And it's not just one or two channels. Now that it might be 5 to 42 megahertz, 5 to 60. Now we're looking at systems going 5 to 85 megahertz. It's the spectrum's getting full in the upstream. So now we don't have much spectrum that we can just throw away. We're using close to the diplex filter, so we definitely need pre-EQ. I always thought lower below 20 megahertz is a lot of impulse noise. And I asked this question to you guys during that panel last year. I said, is there any detriment to running pre-EQ? Like, should I not run pre-EQ below 20 megahertz if impulse noise could negatively affect the pre-equalization? And then I thought, well, if it's lower than 20 megahertz, it's real far away from the diplex filter, but that's not our problem now. It's mostly micro reflections, not group delay. Group delay might be a problem near filter roll-offs and stuff like that, but in the lower frequencies, we still have a lot of micro reflections no matter what. And I remember the one guy, I think from Cable Lab, said, no, I would run pre-EQ everywhere. Do you feel that same way?
Absolutely.
Yeah. So you don't think the impulse noise detriment is enough to turn off pre-EQ?
No, so early on, and that's a good point, John, and credit where it's due, the early implementations of pre-EQ, in fact, you could actually see them in like the post-equalization coefficients where it was constantly attempting to adjust like a nonlinear effect of an impulse noise that was present. And I think it's all just kind of worked itself out where the burst receiver vendors have come up with the appropriate filters so that it's just not they don't whack out like they used to. So in general, I'll say it's I would always recommend using adaptive equalization.
Yeah,
and good question though. Yeah,
I've also had great results with dynamic upstream interleaving in the mod profile when I use frequencies below 20 megahertz. That usually creates the uncorrectable effect to go to correctable effect in some regards. So it actually works out pretty well. It's something that's not on by default, but I usually give a recommended mod profile if people run frequencies below 20 megahertz.
Yeah, that kind of reminds me of if it's raining or pouring outside, run around really fast and you won't get hit as much.
Unless it's going sideways. Unless it's a hurricane.
Yeah, of course. Yeah. Okay. So great segue, and I think your comment about how your early days of doing return sweeps and kind of evolved and connected the dots when we were able to use CPE to effectively do return sweeps for us, and that really changed the game for return setups and return sweeps, in my opinion. It certainly did in my world, and I can't remember the last time I've heard of anybody having to do a return sweep anymore, just to be honest with you.
Now, is that in both the forward and the return, Larry?
No,
or because I mean, the return sweep is something that I think is really going away. Yeah. Forward sweep still happens a lot.
Oh, absolutely, yes. But the point was, that with the intelligence of the CPE and the ubiquitous deployment of all this stuff, I mean, why would you drive around doing things that your CPE can tell you? That's kind of the segue into the next part of the conversation.
Yeah.
That came up with a local SCT I was at, and I said, with full bandwidth capture on the downstream, and we can use that term, right? FPC, full bandwidth capture. It's not copyrighted.
We're good.
I remember that someone was saying generically we're going to call it a wideband capture or something. I don't know. And I felt like with so much spectrum being used in the downstream, with full bandwidth capture, you almost have a downstream sweep everywhere. But if we go to 1.218 gigahertz upgrades, you're probably not going to have carriers there, so you might still need to inject sweep points. Then it comes down to where do you inject those, where do you put the equipment to inject? I mean, Brady and I have talked about this. When we go eventually to remote PHY, now it's all digital out to the node, so you have to inject the sweep points at the node somehow. Because you're not going to have test equipment hanging off the pole, next to the node. So do you incorporate some type of injecting sweeping carrier in the chipset itself? Or do you just use the full bandwidth capture and look at the noise floor as like a sweep trace? I mean, noise does get affected by gain and loss pretty much the same way, right? So if you normalize
great point.
If you normalize it, then you can kind of get sort of apple. It's not really apples to apples, but you get the idea. A delta.
Yeah, absolutely, and that's a fact. But the problem with that approach is that it's actually a great one. We should talk on the side about getting a patent on that. But the problem with that is the filter response across the entire spectrum. It's very difficult to get a flat filter response across the entire spectrum all the way out to 1.2 gig or whatever. So there's a lot of stuff in there you have to normalize out too, which would be again the filter itself. So it's worth looking at. But I'll tell you, we call it a sacrificial QAM. You just put it out in the roll off, and you can basically. And this is a great conversation for how do I use full spectrum 3.0 cable modems, and we're doing this today. It's fantastic to characterize the roll-off of the spectrum where we want to cheat and use 3.1 OFDM channels. If I'm going to put a 96 megahertz wide, OFDM channel in there, what does it look like before I even deploy it?
Of course. You should test the frequency you plan to use with the type of signal you plan to run.
Exactly, but on the so you could just turn it on and use your 3.0 spectrum analyzers to tell you what the frequency response is, even without participating in the 3.1 conversation, if you will. But you can learn a lot about the frequency response and the fidelity of your plant at whatever frequency you're trying to use. But a lot of systems, I'll be honest, they're just sticking a QAM out, calling it a sacrificial QAM out in the high end in the roll-off area, and it tells you a lot. If you're looking for
here's a good question for you. Yeah. I brought that same question up. I'm like, if I want to turn on more QAMs, the CMTSs now are CCAP, right? They have full spectrum capability. So do I turn on more RF? Do I turn on more RF? Is that your phone or something else's?
Sorry, that was me.
So if I turn on more RF, can I do it without being charged a license? So think about that one. That's probably higher above your pay grade. I don't know. But I said the same thing to my own guys. I'm like, I should be, as an RF guy, I should be able to turn on RF that doesn't carry any content and not have to pay a license to turn it on. Because I might want to just use it as a test signal.
Interesting.
You didn't hear that from me, and this is not being recorded, right?
Just to the whole world. Just to the whole world. That's.
I play the devil's advocate.
We'll ask everyone to keep it quiet.
Okay, so my official response is no comment. No, to be honest, but that makes assumptions about your environment, right? You could still be running an old CMTS. You could have a combiner in there. You could have a QAM, an edge QAM. If you could pull a Tom Williams and run a rubidium stabilized, tone out there.
No, you obviously could inject pretty much anything you wanted.
Exactly.
Generator,
It could just be a CW from an analog generator, which doesn't cost you a QAM license.
Exactly. But that's no fun. It's fun to see QAM.
Yes, that looks much better.
No, but
or an OFDM channel all the way out to 1.218 gig.
Yeah, that's money, and we do that here. We'll run, stand up an OFDM channel wherever it is you're running it, and use our DOCSIS population of spectrum analyzers, which right now is just tipped 50% of every DOCSIS device on Comcast footprint has a spectrum analyzer minimum 1 gig of spectrum visibility to it. And so the cool thing about this, and I'll go geeky on you guys, you know what Nyquist theorem is all about. You can instruct the FFT parameters on the spectrum capture engine to hit that thing at exactly the right place at 25 kilohertz resolution bandwidth, and you can sample the OFDM subcarriers with excruciating detail and accuracy. So, if there's a roll-off in there, you can literally see the pilots, you can see the PLCs, you can discern a lot about the performance before you even deploy a single 3.1 cable modem. So there's a lot of intrinsic value in your existing population there.
And you're just talking about the full band capture capabilities of deployed DOCSIS 3.0 modems, Larry. Is that correct?
Exactly. Absolutely. Yes. And so now I'm not saying we don't sweep and we don't balance, but what we don't do is go sweep and balance where we don't have to, right? So think about the operational efficiency. If I have 10,000 route miles, and I'll talk about a little more about that a little later in the show, Brady, but 10,000 route miles, and we use this technique, you can basically weed out 80% of the network that's not of interest. This is perfect from here. So that now you can focus your very limited and high-value resources out in the field to go fix the problems. So spend time fixing problems and not time finding problems.
Sure. So what you're doing is you're weeding it out. You're saying because we don't see any suckouts, we don't see any peaking, we don't see any noise, roll-off, etc. on all of these full band capture modems that are deployed in this X amount of plant, there's no sense in going out and sweeping this X amount of plant because the modems aren't reporting any problems back to us. Is that an accurate assessment?
That would be a foolish waste of time to go sweep perfectly good plant.
Yeah, that's awesome.
What used to crack me up was, we always squab over a dB here and there, and then originally people were balancing based on CW carriers at the high and low end. I'm like, how do two carriers represent your entire spectrum? If you have roll-off on both ends, you could be balancing, changing your pad based on 3 dB low. So now it's all humped up in the middle, which creates even more power and more distortions.
Yeah.
So balancing based on a sweep trace and getting the median or the average power where you need it to be and normalized, that really, to me, makes more sense. If it rolls off, it rolls off. You don't pick the whole thing up just so there's 2 endpoints at 0 reference point. Now you're creating a hump in the middle. So I've been doing it for a long time, and I always thought that, looking at the sweep trace as a balancing technique was much better than, just relying on a couple CW carriers.
Yeah, or you're missing lots of suckouts in between. And I think like what Larry's talking about is exactly the huge benefits that we're seeing in advancements in PNM, where we can use full band capture modems to see huge areas of the plant. We have visibility all the way to the subscriber's home, not just to a sweep point that might be off of an amplifier or a tap, but we're seeing right into the subscriber's home any impairment that may exist between the head end and many, many, many individual subscribers' homes. So it's huge.
It brings up a good point too. Is originally I thought this whole talk, and I always thought PNM. We think PNM is upstream pre-EQ, but PNM is everything now, right? It's downstream, it's upstream, upstream spectrum analysis, full bandwidth capture, pre-equalization. I think the modems, the 3.1 modems, can generate an upstream sweep trace practically, like a sweeping carrier. I've even used that in the lab one time to prove that the modem itself, its internal filter was bad. Because I had 8-channel upstream bonding, and upstream 3 and 4 were sucked out, and it was the internal filter, had a 4285 filter that was kind of overlapping itself. It was sucking out right where the cutoff, where the rollout, or where the crossover was.
Yeah, crossover.
Yeah, so it was kind of interesting. Is this is the type of functionality we have in the modems now, and it's how do we utilize that? What else do we got in the 3.1 modems? Where are we going with this this hangout, Brady? I'm trying to segue us.
So, basically, we keep on getting more and more advanced features. It's what do we want to talk about next, or what do we want to reveal next?
Let's talk about the upstream. This is the secret sauce. It's the Achilles heel of cable. I'll share some numbers with you just off the cuff here. From the maintenance technician perspective, not necessarily that we're talking bucket trucks, not vans. It's upwards of, conservatively, depending on the area, 70%, upwards of 85, 90% of the time that a network maintenance technician is spending out in the field is in the pursuit of return noise and mitigation, of course. And by mitigation, that may or may not mean fixing it. Let's just be real frank about it. A lot of times we can't get access. Maintenance tech may not have, fulfillment tech. A maintenance tech might not want to go into a house. House is most of where the ingress comes from. That is the Achilles heel of cable, and there's a lot of inertia on that, and how we chase it and what we do about it is evolving quickly. So let's shift gears to upstream in general.
Okay. So I think we're doing a lot of things with upstream. We do upstream spectrum analysis. We use the CMTS to do that. We've just pushed through a new ECO, a cable labs, that's part of the DOCSIS 3.1 specification that will allow us to have a standard MIB for all CMTSs to do triggered upstream spectrum analysis with all DOCSIS 3.1 CMTSs. So that's nice. It gives us everyone has a common MIB, a common software development platform for across all CMTSs. Now there will be some time before vendors can implement this. So there's some excitement there. We'll have that capability in it. And what's that?
I assume remote PHY as well.
So that is a really, really good point to bring up, John, is, it's one thing to have a head end where all signals are culminating at, and you can put whatever type of equipment you want. But when you talk about a remote PHY, where you have, and if you don't have an understanding of a remote PHY, you basically are taking the RF portion and the MAC portion of your CMTS and putting it out in a node, right? And you're taking your RF signals at that node, at the fiber node, you're converting them from RF back to data and then transporting that data optically, no longer as analog, but as true digital data back to your CMTS core. So at this point, if you want to do any return path analysis of where's my noise coming from, it has to be done at that fiber node. So now, like to your point earlier, John, we can't be hanging a bunch of test equipment off of a fiber node. We have to be communicating.
You're put a path track out there.
Yeah, it's going to be, it's an expensive place to put it. So now we want to be able to communicate with that remote PHY. If we know we have a noise problem out there, maybe we have some really high uncorrectable code word errors and we believe we have noise ingress, we want to be able to communicate with that remote PHY, either SNMP or IPDR or maybe some other communication method, and say, if my return is 5 to 42, 5 to 85, or even 5 to 200 megahertz, where's the noise at? What type of noise is it? Is it impulse noise? Is it HPNA? Is it some other type of noise? I want to be able to see it, just like using a regular spectrum analyzer or return path monitoring system. And that's what this basically new ECO that went through gives us the ability to do, to monitor that remote PHY without having to hang heavy and expensive test equipment on with a fiber node itself. So this is awesome capability.
I mean, it's good to hear, but I mean, I have experience with the CMTS spectrum analysis, and I told people it's never meant to replace a real spectrum analyzer because of the how quickly it could capture, say, impulse noise. Because with the spectrum analysis, it was SNMP based. So how quickly are you getting SNMP responses? So getting that SNMP and how quickly is it? What is the resolution bandwidth, the video bandwidth? I couldn't do zero span mode. So I don't know if this ECO addresses how quickly it can capture. Can it really capture impulse noise? That's my point. I never could really capture impulse noise before.
Yeah. If you're lucky. Hey,
go ahead, Larry.
If full fairness and disclosure, John, can you talk just a minute on your early involvement with, I believe it was the CBR, or no, sorry, what was the tool? CBT, yes.
Yeah, Cisco Broadband Troubleshooter. So basically it was Cisco proprietary MIB, but we've given it out to a lot of people.
Thank you,
and it really was, the information from the Broadcom or TI Intel Upstream chip, and then making a GUI to pull that information. And I've even, to get a faster response, I could set my SNMP to 0, polling 0, meaning do SNMP as fast as I could. But it was still an FFT. It was still grabbing the information, and it was great for seeing the spectrum. It was great for tagging a specific MAC address. And because the CMTS does all the timing, you could also say, show me the upstream with no bursts. So that was a great functionality because, PathTrack couldn't do that. PathTrack had no idea about timing of mini slots, but the CMTS does. So you could say, you know what, show me the ingress under the carrier. I've even used the CBT to say, let me show you the upstream port with no traffic. And if I saw traffic, then I knew it was bad timing, or it was actually upstream that was meant for a different port and poor isolation in the head end bleeding over to the wrong port. So I was able to kind of make some, deductions from seeing and knowing how it worked. But I was never able to capture impulse noise. Maybe it would once in a while. And the one thing I was always asking for that I never could do, and maybe Brady can mention if we are going to do this, I don't know if the chipsets will do this, I want to go below 5 megahertz. I need to see AM radio noise that's causing laser clipping. So I want to go down to 0 or 0.5 or 500 kilohertz or something like that, and then all the way up to, say, 85 now. I mean, we can do up to 85 now. And even on the chipsets we have installing now, we'll go to 204 megahertz because they're DOCSIS 3.1. So I don't know if that kind of covers what you're after.
Absolutely. No, so it's a great history about, and here's kind of segue to talking about using the CMTS burst receiver to do spectrum analysis. The capability has been there for a long, long time. What year would you say, John, that you started CBT, or was it first came to your attention?
Yeah. Shit. I've been there at Cisco 15 years now, and that was there probably 10 to 12 years. Yeah.
Now, so Brady, as a not intentionally plugging your product, but Nimble does that exactly that, right? You expose the CMTS burst receiver MIPS to offer kind of a low-cost intrinsic spectrum analysis using the burst receiver.
Yes, it's exactly correct. And some of the things that John mentioned, like being able to trigger on a SID or a MAC address, or a time when no modems are transmitting, so you can see just the noise floor. All that functionality is there. To John's point, right now with the existing CMTSs, you can't trigger on burst noise. One of the things that we've done in the new MIB for DOCSIS 3.1 is that you have the ability to set thresholds. So ideally, we can capture that burst noise that we can't do in DOCSIS 2.0 or 3.0 CMTSs.
Yep. And the reason that I ask is we do this at Comcast too. It's obviously very intriguing to be able to use a burst receiver because then, in particular, that the facilities real estate is really getting into a crunch now that we're kind of going through these architecture migrations and these things. Our head ends are basically golden space now. So rack space is important, and we really like having the CMTS burst receiver's knowledge of mini slot timing, and for the reasons that you mentioned. It's pretty cool to be able to see under the carrier truly at exactly the moment when there should be nobody transmitting. And so you don't have to do min-hold tricks and all this other stuff that we've done over the years, to try and perceive, things about the spectrum. But I'll be honest, that has limitations too. Burst noise is one of them. We have dynamic range problems, and depending on how people set up their CMTSs, what the nominal level of the receive level is set up for, people padding or no padding, and it's just all over the place when you have such a diverse environment at the burst receiver. So, we're having challenges with that too. But very much looking forward to the 3.1 hooks that are coming with. It's just going to be extraordinary, very much game changer from the upstream perspective. One other issue, and this I think is probably segued to the other stuff. What else is out there, Brady? Using the CMTS is fantastic, but that doesn't solve for fiber deep nodes where now we're starting to do pretty heavy combining at the CMTS ports. Instead of having to drive out to 1 or 2 nodes basically to isolate the ingress point or the leg of the node, geez, now you got to go out to minimum 4 nodes before you can even begin to troubleshoot out in the field. Right.
So I'm going to share just a couple of slides here. We're going to be doing a press release at Cable Tech Expo. So I don't want to go into too many details here on this, but I want to share this because it's some really cool stuff. We'll just call this for now PNM remote monitor. So if you can, you guys see what I have on my screen?
Got it.
Yeah, got it.
Awesome. So we have this little silver box here, and it's a cable modem, but as you see, it has additional ports on it. And the little cable modem you would put into an amplifier. So one of the port is going to go, this main cable modem port here is going to go into a test point on the amplifier where it can see both downstream and upstream. The other ports are going to be monitoring test points in the amplifier itself. So you can see the upstream and also, more importantly, the downstream. And so this would be that actual device installed in an amplifier. And so again, this is just a cable modem. It's a full band capture cable modem. Port 1 here would be the cable modem port itself. So here, what I'm showing here, I just did a screen capture on it. I didn't want to do a live demo because that always creates problems and takes a while. And so I thought I'd do a screen capture. We can see we have pretty low noise floor on this port, down at -50 dB MV, so we have pretty decent dynamic range. You can see the forward channel here. So this goes all the way up to a gig. So to your point, John, we can see, whatever the forward channels are and the return channels. And then we can also see the modem temperature. So this is in degrees Celsius. If you click on it, it turns to degrees Fahrenheit. It's nice to see the basically so this is installed in a fiber node or maybe a trunk amplifier, bridger amplifier. You can monitor the temperature while you're going. And now we want to look at one of the other ports, and we've been told that there's a bunch of modems out on port 4. So when we look at, the next slide is going to show you the difference between port 1 and port 4 on this amplifier, and we're going to see that the noise floor goes up pretty significantly.
Wow.
So now this is port 4 on this same exact amplifier. So like to what Larry was saying, normally if we wanted to compare the noise difference on 2 ports of the same amplifier, you would have to go out and pull the pad on this amplifier and see what the difference is back at the CMTS. But now if you install this little tiny silver box, it's a very tiny modem, and this modem is powered off the power pack in the amplifier itself, you can just toggle back between port 1 and see, hey, port 1, really low noise floor, no problems. If I could also see the forward pass signals. Port 4, this is why my modems are offline on port 4. We've got a really high noise floor. So
how are you plugged in? You're plugged into the test points?
Yeah, we're plugged into the test points in an amplifier.
Bidirectional on the outside of the diplex filter? I guess it almost seems like you'd have to be plugged into an upstream reading and a downstream output test point. It's
going to depend on the amplifier. Some amplifiers have bidirectional test points, so you're going to see the forward and return. Some amplifiers, you're just going to you're going to plug into the return path test points, and so then you're only going to see the return on it.
I actually wonder if you had that case, if you just plugged into the upstream reading test point, and then you kind of eyeballed, you assume a certain amount of isolation on a diplex filter, you would still see the downstream, right?
Yeah, you're still going to get some downstream level, but it's going to be, on a 20 dB down test point. So you're going to still see some. And this is just an example of that same port 4. You can see, not only is there a lot of ingress noise, but there's something serious going on with the forward on this as well. So it's impacting both the return, letting a lot of ingress in, and it's also seriously impacting the forward because you can see there's a good bit of ringing going on here, and so that's
just brilliant, Brady.
Tremendous diagnostic capability without ever having to open up the amplifier. I mean, we know there's a problem on this one port of the amplifier. The other ports are okay. So right away we have the ability to make a diagnosis, know which amplifier and which leg of the amplifier is having the problem, all from the comfort of your desk, and then send the right person to the right place.
And to be clear, what's really intriguing by this example you pose here, Brady, is that the age-old Achilles heel of cable is that port 4 right now, you have a port level resolution of where the noise is. Before this kind of a solution, you would have a node level resolution, or at least at the combining level, you'd see the noise getting in, but you would have no idea which leg is getting in. So that from the field perspective, it's a trip out to that active. Well, actually, you start at the node and you begin breaking it down to the leg. You're disrupting your customers by pulling pads, and you're driving trucks to places, dividing and conquering and blocking and tackling, and then eventually you get there. This short circuits all of that stuff.
Yeah, so we're super excited. There'll be a press release about it right at Expo. So you'll find us on the show floor demoing this product at Expo.
Very exciting. I'll be there.
Yeah, I mean, it's interesting because we've tried to push status monitoring forever, and now I think maybe with the technology and lower cascades and the importance of everything and the cable modem and the inexpensive way of doing it, this makes a lot more sense now.
Yeah, it's super cheap. It's commodity technology, so.
Yeah, timing is everything, and it's funny. So I'll be just honest with everybody. I've seen this before. I'm in love with it. It's fantastic. And my understanding is we have seen folks with this thing running as low as 1.5 watts. The heat signature is basically non-existent if you have it mounted properly to the shell of the amplifier or node or wherever you're going to put it. The cost is commodity-based. It's mind-boggling, but it reminds me of kind of when the iPad took off, right? The iPad was not the first tablet ever invented. There have been tablets since the 80s, but the technology wasn't right. It took the stars aligning for touch screens and speed and doing away with, the stylus, and it took everything to get right before it basically transformed the way we compute. And I see this as being one of those opportunities in cable. Just the timing and technology is finally right. So, very exciting.
Hey, Brady, was there a certain resolution bandwidth setting on that, or is it hard set?
This is a cable modem, so you can go. Right now, we have a program to go as low as 30 kilohertz. The default is 100 kilohertz, or you can set it at 300 kilohertz. Those are our 3 default settings. But just as you can change the bin size on it using the standard DOCSIS MIBs to change to other resolution kilohertz bandwidths if you would like to.
Nice. Oh, very nice. So let's take a devil's advocate view here. I know we're pushing up on close to an hour, but I see trouble with this, and like John alluded, status monitoring and transponders have been around for a long time, and arguably, some places and systems have just let them lapse and haven't used them, and just because you got it there doesn't save the day, right? You have to integrate it with your operations, and it has to become a thing. What makes us think that this is really right? What makes us think that we're going to start sticking things out in our plant, activating them, and now have yet another point of maintenance and power consumption and thermal considerations that aren't going to someday break or become out of date, that need to be removed and maintained? What makes us think we're going to actually deliver the promise this time?
So I think one of the things that we have going for us is that we already have some proof of concepts out there in status monitoring modems that are in power supplies. So we have proof that this works because we have a lot of power supplies with cable modems in them that are being used as full band capture devices today. And we have a lot of cable modems out there. I mean, people are buying cable modems and putting these next to cable supply or power supplies, commercial cable modems, because they don't want to pay the little bit more money for the status monitoring, sort of ruggedized versions that come with a power supply. So that kind of gives me a really good feeling that if that works, and we're buying DOCSIS 3 status monitoring devices, putting them in power supplies, and those are working really well, we're getting good data off of those, then this is the next evolution where we're taking a cable modem, an industrial grade cable modem, putting a 4-port switch on it, and now putting it in an amplifier, this is just taking it one step further.
It's genius.
So it's going to be, I believe, solid. Will we have some growing pains? Probably. Will we overcome those growing pains? Absolutely.
Fantastic. And so to that note, I will say, I've seen that at Comcast too. We have really fantastic status monitoring. We have transponders, we have systems. But one of the motivators that I've seen individual technicians and systems taking that, put a commodity DOCSIS box out there as a measuring point, isn't necessarily the cost or the trouble or expense. It's really because it seamlessly integrates with all the tools we got already. Yeah. Right? If you drop one of those out into a power supply, and it's it now magically participates in all of our Comcast tools, Spectra, Flux, Last Tower, and it becomes basically kind of a non-event to extend the capabilities of the network monitoring without having to swivel to yet another application just because it's plain old DOCSIS.
Yeah, to your point, I mean, we've had many things in the past, like you said, tablets and stuff that didn't work because they weren't part of a standard. Apple's iPad worked so well because it was part of the Apple ecosystem. It worked with iTunes and everything else Apple. This works so well because it's part of DOCSIS. It's part of the DOCSIS ecosystem. It works with SNMP. It works with all the tools that you currently have. That's what makes it so elegant.
Exactly. I love it. Thanks for that, Brady. Anything else?
I don't know the whole functionality of it, Brady, but I'm thinking, as a cable modem, I'd like a cable modem to see on the downstream, between -5, +5, and I'd like to transmit about 45. So if you're just plugging it into a node through a 20 dB test point, and you don't put extra padding, it could be transmitting at, say, 25. If it goes off the rail at some time, it can go up to 55 and then cause laser clipping of itself, So I always like to keep my modem transmitting close to 45 so there's not much range left if it does go kind of crazy, it starts babbling. So 45, 48 would be good. But I'm thinking also you can't control which MSO, where they put their DOCSIS channels, on the low end or the high end. If you come up a downstream test point, you're going to have tilt. I think I'm going to call it your black box, silver box. Your silver black box. Your silver black box. I almost think you should put a cable simulator in there because you're always going to see tilt from the downstream test point. So you could probably put 10, 12, 15 dB of cable simulation to flatten it out and then padding in your black box so that basically all nodes are probably going to come out, distribution levels nowadays because there's really no trunk line. You could probably figure it out, right? So I don't know what you're doing about that. If you're going to have pencil pads or something inside that black box, maybe go back to diddle sticks. Bring back the diddle sticks.
No, it's not too bad. I got an idea. Let me throw 2 cents in. Let's go with software. You can normalize that. You can unsell with software if that's really a requirement. And too much data is a good thing.
Yeah, but you got my point, right? I mean, hitting a decent downstream level between -5, +5. I don't want this device. It's a cable modem. But I've seen where cable modems are not set up properly, and they cause problems. So I don't want this to cause a problem.
Yeah, I understand what you're saying with transmitting too high. That's something that can be done with proper installation guidance.
But as Larry just mentioned, maybe if you had software-controlled pad EQ internally, then you could adjust whatever you want.
Yep.
I don't know.
Okay. So I love this. What you have, let me recap this for you, make sure I interpret this properly. Basically, a module. And it looks like you can power it and connect it up as a DOCSIS. It's just honey, I shrunk the cable modem into a nice tight little box. What precludes you from sticking that into a power supply cabinet?
So it goes into a power supply cabinet. Could be, just like you're saying, a transponder, monitor your downstream, your upstream. You can put this anywhere you'd like as long as you have 24-volt DC powering, a wall wart even.
No kidding. So, in theory,
you have no RF at the power supply cabinet. There's really no RF at the power supply cabinet, right? I mean, we're trying to look at RF, aren't we?
You can run a coax drop.
Exactly. I mean, from a tap maybe or something like that, right?
Yeah.
Well, we do that for transponders today.
Okay.
Yeah.
I just see that. I see it more as a node functionality, best bang for your buck, being in the node.
Okay, how else could you could put it in an amplifier that would give you, let's say hypothetically a use case. If I have a N plus 4 or 5 cascade, and I'm busy with a really noisy node, and it's in high density residential area with MDUs, and loose connectors are killing me all the time, and I'm rolling trucks constantly, pulling pads, trying to isolate legs on this N plus 5 with all these through legs and such. And there's tons of splits, and it's just a total pain to maintain this thing and constantly mitigate noise. Hypothetically, couldn't you embed one in every amplifier and the node if you really wanted to in the cascade?
Yeah, absolutely. And I think you're bringing up another point I hadn't considered before, where MDU environments, where you have big clusters, big closets full of connectors and splitters. Actually, an MDU might be a good place to put these for monitoring, where you could cluster many of these together in a shelf. So these become like awesome monitoring systems.
That's it makes MDUs have maybe 3 or 4 risers, right? You might be able to segregate.
Absolutely.
Yeah, so it makes MDUs are notoriously difficult to troubleshoot, especially like with a P&M system where it's difficult because your spans where you have echo cavities are very, very short. So having something where you can start monitoring different floors and different legs very quickly and troubleshooting problems in high density buildings, multi-dwelling units, this becomes something that's, because it's low cost, it doesn't cost a lot to deploy many modules in this. So it becomes a very, very, the potentials on this become limitless for deploying it.
Yeah, thank you, generic module. We love it. Let's think about what you said. MDU is a fantastic use case. I just kind of posed it, but I didn't think about it that way. But you're right. We could put it on a rack in the cabinet in an MDU complex and immediately just automatically start dividing the problem into spans and legs without having to disrupt the entire complex.
And while you're rack mounting it, you may also want to put it in your head end or your hub site. And so there's many places that if it's rack mounted, you could do a lot with this device.
Yeah, that's fantastic. So and not just upstream, but also downstream, depending obviously on the capability of the test points. But man, could you imagine a head end instrumented full test point upstream and downstream visibility in real time?
Yeah, it does. Up to 1 gigahertz. It does forward path and return path monitoring all in one device.
Unbelievable.
So
yeah, I mean, it might not work in line extenders with flat lids, right? Because there's no space. You're probably talking more like amplifiers that have a lid that has space in it.
Yeah. I don't know, Brady. How thick is that thing?
It's shy of an inch. I think it's maybe three quarters of an inch or less. Actually
thick.
It's maybe even less than 3.
The one I saw was a 1/4 inch thick.
Oh, is it a 1/4 inch? Okay, I haven't measured it. So yeah, it's very thin actually. So it probably will fit in the line extender lid, but I don't know.
All right, I'm being coy. I've seen it in a line extender.
You have?
Yeah. I mean, not all line extenders, but some will work. Yeah. It's pretty cool.
Very nice. So as you mentioned, being devil's advocate, you talk about it's rack mount, it has extra test points and all that, but what's going to keep someone saying, well, why would I put this in the head end when I just put a modem in the head end? It's a modem. I have a modem. So why would I put this in? What does it give me that's more so than just a modem?
One thing that I noticed about at least 3 of those ports on the RF switch is they're uninhibited by the diplex filter that you do not get from a cable modem.
Yeah, that's what I was leading to.
Yeah, that's the secret sauce, is you don't have the diplex rejection in the return band.
It's also density and power, because you've got multiple ports. You'd have to have multiple modems. You don't have a diplex filter there, and they're very low power.
Yes.
Now, if you do a head end or a hub site, can it be 110 volt? Can you plug it in with 110 volt?
Well,
you would have to just have a power supply to feed DC to it.
Okay.
That might be tricky.
Yeah. Where'd you come up with the power supply?
Oh, geez, that's funny. You guys are great. I got to be honest with you. I know we're coming up on an hour. I still have a little time, but it's such a thrill for me to be here with you guys. I've known y'all for a long time. We're all part of birds of the feather with this P&M business. I can always count on seeing all of you at Expo and the Comcast conferences, Cable Labs conferences, and we can talk for hours and hours on this stuff because it's all of our passion here. So it's really a pleasure to be here with you. I've known you guys for a long time. I'm huge fans. Thanks a million for inviting me to.
And Larry, you're doing a great paper at Expo this year, right? It's
thanks. I didn't want to do the cheap plug, but because you brought it up, yes. Thursday, the last day. Thanks SCTE Council for doing this to me. But I think they like to do a bookend kind of thing. It's the very last day, the very last thing on Thursday, and but it's cool. It's kind of an institution. It's the P&M, conversation. And this year, I'm going to be doing a pretty comprehensive case study, which will talk about a lot of the stuff we've talked about here. A lot of gory detail about the financial aspects and the things that have been traditionally hard to answer. We put a lot of energy into that about cost versus benefit, P&L, barriers of adoption, and all of these things. So I would encourage anybody to come say hi. If you listen to this podcast, mention it. I'd love to hear that. I know there's thousands of people that do tune in occasionally to your great show, Brady.
All right. I recommend everyone catch Larry's show or Larry's presentation at Expo. Stay for the last day. John, I think you and I are both out this year on. We're not presenting, right?
What?
No, I didn't submit anything.
Yeah. So we're taking this one off. So we'll make sure to catch yours, Larry.
You just come up on stage with me because you deserve as much credit because you guys are pioneers, and I think.
Larry, are you going to cover DOCSIS 3.1 stuff as well for P&M?
It's like a couple of pages. There's some great stuff. Another plug for my colleagues at Comcast. Great friend of mine, Rob Thompson, will be going over kind of a very novel, not DOCSIS 3.1 specific, but that's on the first day. So I said bookends. Don't come in late and don't leave early because you're going to miss all of my favorite stuff. Rob Thompson's going to be doing some stuff, but Maurice Garcia is doing some really fantastic work at Comcast and in the same session with Rob Thompson on Monday. So don't come in late. Go see Rob and Maurice, and then stay all the way through and come see me. And by all means, anybody out there, we're all friends here. Look me up. I'd love to go have a beer and a pizza with anybody who loves P&M as much as we all do here.
It's supposed to be a pretzel and a Philly cheesesteak.
Pretty much.
All right, guys. Hey, thanks so much for your time. Great information. Have a great weekend. We'll catch you later.
Ciao, P&M.
Thanks, guys.
Thanks a bunch.